Alright, welcome back, guys. We're going to be covering 3.7, and this section, at least at the time of this recording, is the last section before your first exam. Okay, and you can see here it's titled Systems of Inequalities in Linear Programming. So what we're going to be doing is we're going to be graphing inequalities, much like we graph equations or functions, however you want to refer to them. And remember, when we graphed an equation, guys, all of the points that made up the graph, whether it was a straight line, if it were, hey guys, yeah, okay, sorry about that. Yeah, anyway, let's see. Oh, right, yeah. So when we graphed an equation, if you remember way back in section 2.1, all of the points on that graph were solutions, okay, to that equation. And you know, every single one of those points had a value for x, had a value for y, and those values would make that equation a true statement. So what we're going to be doing today is graphing inequalities. So, for example, if you look at this one right here, this looks very similar to what we've done previously. You know, if this had said y is equal to x plus 2, we know that would be a linear function, right, or a linear equation. The difference is that this is not an equation, this is an inequality because of this symbol here. And so that changes the nature of the solutions. Instead of the solutions lying just on that line, okay, the solutions, they may still lie on the line, but they're also going to be on either side of the line. So it could be referring to all the ordered pairs that are above the line. Okay, all of those ordered pairs would make that inequality a true statement, or all the ordered pairs that are strictly below the line. Okay, we'll talk more about that here in a minute. First of all, you know, the term inequality itself just means not equal. And in math, inequalities use symbols, and that's what we're going to go over first. Okay. But let's look at this first paragraph. It says these are similar to graphing linear functions. And by the way, guys, we are only going to be looking at linear inequalities. Okay. There's all kinds of inequalities, quadratic inequalities, cubic, whatever. But we're just looking at linear inequalities. Except that instead of just a line, we're going to have an entire region of the coordinate plane that's shaded. And that region is going to represent the solutions. Okay, so the solutions are still ordered pairs, and there will still be infinitely many of them. They may not be just the ordered pairs that make up the line. Okay. All right. So, you know, to denote an inequality, we have to use symbols. You guys know math is made up of a lot of symbols, isn't it? And so we're going to see symbols like this. This is, well, I can write these down. So if you read an inequality from left to right, which I would recommend that you do, then this inequality symbol is we're going to refer to as greater than. Okay. And all this means is if we want to use this symbol in some mathematical statement, what we have on the left-hand side needs to be greater than what we have on the right-hand side, strictly greater than. And then similarly, this symbol right here means less than. Okay, so whatever I have on the left-hand side needs to be strictly less than what's on the right-hand side. I'll give you an example of each of these. So 10 is greater than 5. Okay. Or an example using the less than symbol, let's see, we could say, well, I don't want to get into the negatives because we could say that 5 is less than 10, okay? These are true statements. Both are utilizing inequality symbols. Now let's talk about a couple other ones. So I said here this one is strictly greater than. Well, we also have one that is referred to as greater than or equal to. Okay, so it's this symbol right here. It's the greater than symbol with a bar underneath it. So the bar means or equal to. I'll write this: greater than or equal to. So an example, I'll give you a couple examples on this one, could just be simply 10 is greater than or equal to 5. Okay, there's actually two conditions there. What's on the left-hand side has to be either greater than or equal to what's on the right-hand side to satisfy this inequality, or to make this a true statement. Okay, so 10 is clearly greater than 5. But also this inequality right here, 10 is greater than or equal to 10. That's true as well. Because although 10 is not greater than 10, it is equal to. Okay, so remember, there's two conditions. It just has to satisfy one of those, and it will only satisfy one. And then lastly, guys, very similarly, we have the less than or equal to. Okay, so an example here, a couple examples here would be 5 is less than or equal to 10, or 5 is less than or equal to 5. Both of these are true. Okay. All right. Now, why would we be interested in inequalities? Inequalities, guys, are used. They're, a mathematical tool like everything that we're learning. They're used whenever we're trying to model or represent a scenario in which there is a boundary or limit. Okay. So think about things in your everyday life for which there are limits. So there's a speed limit, right? So you want your speed. I guess theoretically, let's say the speed limit is 70 miles an hour. So you want the velocity or the speed of the automobile to be less than or equal to 70, right? You don't want it to be greater than 70, because then you're violating the law and then you run the risk of getting a ticket. Okay, I'm taking practicality out of this, by the way, because most people exceed the speed limit. Another example would be, let's say we are budgeting. Okay, we want our expenses to be less than or equal to our income. That would be an ideal situation, right? Or you could say we want our expenses, you could give it a specific amount. We want the expenses each month, and those expenses could be made up of several things. Okay, food plus gasoline plus rent plus insurance needs to be less than or equal to a specific amount. Okay, so those are just some examples in which you could employ that concept of inequality, greater than or equal to, or less than or equal to, etc. Okay. All right. So now let's talk about how can we graph one of these inequalities. And when I mean graph, I mean represent the solutions, all the solutions to this inequality graphically. Okay, the way we graph a line, a linear equation or function. All right, well, for the most part, guys, it's just like graphing a linear function. Okay, now you could make a table if you want, the way we did back in 2.1. But because all of these are linear, there's an easier way to do this. If your inequality is in slope-intercept form, we'll forget about the inequality symbol here for a minute. Okay. Meaning, as long as it's solved for y, you can look at the two numbers here. You can look at the number b. This is called the y-intercept. It says this further down in the notes. That value, whatever's sitting in place of b, 2 in this case, that is the value at which the line will cross the y-axis. Okay, its coordinates, the coordinates of that point are technically 0, b. The x-coordinate will be 0, because for it to cross or to be on the y-axis, the x has to be 0. And then the y-coordinate of that point will be whatever this value in your inequality is. Okay, and then furthermore, the m represents what we refer to as the slope of the line. So m and b are going to be numbers. Okay, and when it's written in this form, it's referred to being in slope-intercept form. Okay, now, all right, so what I'm going to do is actually go ahead and put a point at 2 on the y-axis. Okay, now remember, this is a linear inequality, so to draw a straight line, I just need one more point. How do I find that other point? Well, you know, you could, well, yeah, so initially you're going to treat this as if it were an equation. And you're going to graph that equation, or treat it like it's a function, and graph that function. Okay, so you could pick values for x, see what those y's are, and plot those points, connect the dots, the way we've done previously. But if you're using the y-intercept and the slope, then you're going to plot the y-intercept. It'll be a point on the y-axis. And then you look at your slope. The slope is the steepness of the line. That'll tell you how to determine where that second point needs to go. All right, so what's the slope in this one? Because there's not a number in front of the x. Well, there is an understood 1. Okay. And what does the slope describe? It describes the steepness. Well, how do we define that in math or graphically? It's what's referred to as rise over run. You may have heard that before. In other words, the change in y versus the change in x. The vertical change over the horizontal change. Okay. All right. So what we want to do here, because the slope is defined, given using this fraction, we want to make sure we have the slope written as a fraction, if it isn't already. So if I want to make it a fraction, I just put it over 1. Okay. So the slope is 1 over 1. So that means what we're going to do is we're going to start at our initial point, and we're going to rise 1, and we're going to run 1. Okay. Now when I say run, that means horizontally. We're always going to go to the right. If your slope is negative, you're not going to rise, you're going to fall, but you're still going to run to the right. Okay, so I'm going to start right here, and I'm going to rise 1, I'm going to run to the right 1, and it's going to put me right there. And that's how I find my second point. Okay, and then I can connect the dots. But because this is an inequality, I need to be careful in how I draw my line. If this is a strict inequality symbol, okay, let me put this here in the notes. The strict inequality symbol is either strictly less than or greater than. Okay, but a non-strict inequality symbol has the inequality component, so less than or equal to, greater than or equal to. So if it's a strict inequality, you get a dashed line. Okay? And if it's a non-strict inequality, you get a solid line. You may be saying, oh, well, why? What's the difference there? Well, let me go ahead and draw this dashed line here, because this is a strict inequality. And we'll discuss why that is the case. Okay, I'm going to draw a dashed line just like that. Okay, and now I need to figure out where to shade, and then we'll talk about the difference between these two. Okay, all right. Well, remember what we're doing here is we're graphing all the solutions to this. So the region that contains all the solutions is either going to be above this line or below this line. So mathematically, the way to approach this is you just choose a point. Could be anywhere. And that point's going to have an x and y coordinate. You plug those values in here, and you see whether you get a true or false statement. If you get a true statement, the region from which that point came is the region that you shade. That's the region that contains all the solutions. If you get a false statement, it'll be the other region that you shade. Okay? So that's the way you do it mathematically. And I'll do one like that. So let me just arbitrarily choose, I don't know, I could choose this point right here. Okay? That could be my test point. Its coordinates are 3, 0. So its x is 3, its y is 0. So I would plug these values in to my inequality. My y is 0. My x is 3. Just recopy everything else. And let's see what type of statement this is. 3 plus 2 is 5. So this says that 0 is less than 5, and that's a true statement. So because that's a true statement, that means this point, which is representative of all the points in this lower region, is the solution region. Okay? So I'm going to shade this, actually no, let me get the marker. I'm going to shade this in yellow. So that means this entire region down here, below the line. Okay. And so what would have happened if you had picked a point in the upper region? Well, it would have given you a false statement. And so that would have told you that this region was not the solution region, therefore the other region must be. Okay? All right, now that's the mathematical way to do it. The way that I like to look at it is, if it's already in slope-intercept form, look at your inequality. If it says less than or equal to, you shade below the line, which would be down here. If it says greater than or equal to, you shade above the line, which would be right here. That's kind of the way I see this. And that's the way I'll be determining this from here on out, even though it's not really mathematical. Lastly, what's the difference between why, in this case, do we get a dashed line and not a solid? Well, the solid line would mean that the solutions are not just in this region, but are also on the line. Okay, and so that has to do with this inequality symbol. Here it says that y is strictly less than x plus 2. Okay, so any points on this line, the x and y coordinates of those points would be such that y would be equal to x plus 2, and not strictly less than. Okay, so we only use the solid line to include the points that are on the line when we have a non-strict, if it has that equality component. Otherwise, we use the strict, the dashed line. Okay, so this is just showing us that any point in this region that I've shaded would be a solution, would make this inequality true. Okay, and any point on the line or above would make it false, would give us a false statement. All right. Well, I spent a little more time than I had wanted to, but on that first example. Anyway, let's look at example 2. Okay, so example 2, it just says graph the inequality, or in other words, graph or shade the region that contains the solutions to this inequality right here. Now look at this one, guys. This one is not in slope-intercept form, is it? Okay, so let's put it in slope-intercept form and then graph it the same way we did that first one up here. Okay. All right, so I'm going to recopy it down here. 5x minus 4y is greater than or equal to 20. Alright, so I need to move my x term over, so I'm going to subtract 5x from both sides here. So this will leave me with negative 4y is greater than or equal to, and then these are unlike terms, so just recopy them, but put your x term first. And then to get the y by itself, we need to divide both sides by negative 4. So, solving an inequality for y is much like solving an equation for y, except there's one thing you're going to do different on certain occasions. So we'll end up with y, and over here, these two negatives turn into a positive, but it's going to stay a fraction, 5/4 x. Right here, however, 20 divided by negative 4 is negative 5. Okay. Now, whenever you're solving for y and you either divide or multiply both sides of your inequality by a negative number, then you've got to flip the inequality symbol. Okay. So instead of this remaining greater than or equal to, it is going to become less than or equal to. Okay. And this is what we're going to use to do the rest of this. Now, you might be wondering, okay, why do we flip it? Well, what happens when you multiply or divide something by negative? What happens to its sign? It changes. It flips. Okay? And so that's why we have to flip that inequality symbol. Alright, so now we've got this one in slope-intercept form. So we're going to treat it like it's just an equation. Y equals 5/4 x minus 5. It's in slope-intercept form, so that means that my y-intercept will be the point 0, negative 5. And my slope, m, is 5/4. Okay? Alright, so I'm going to start by putting a point at negative 5 on the y-axis. This is where my line intercepts the y-axis. And then I'm going to let the slope dictate where I go from there to arrive at my second point. So it's positive, so I'll be rising and running. So I'll start right here, and I'm going to rise 5, and I'm going to run 4. And it puts me, interestingly enough, right on top of the x-axis. Okay. Now, what kind of line? Well, this is a non-strict. This says less than or equal to. So that means all the points on the line are included. So I need to draw a solid line. Okay. Now, where do I shade? Well, you could pick a test point again if you want, but look at our equation here. And by the way, guys, you have to reference your your inequality in slope-intercept form. Don't look back at the original. Okay, we're not using this one anymore. It's got to say y, and then this says less than or equal to. So because it says less than, that means I need to shade below the line. So below the line would be this, whoops, we need to make that stray mark, means that would be, well, get it eventually, this region right here. I don't know why that keeps happening. No, I'm just going to leave it. Okay. That region right there. Okay. So we'll just ignore that. I think that's a glitch in the software here, but Anyway, so this region right here and all the points that make up the line, all of those ordered pairs would make this original inequality a true statement. And guys, you could try it. You could pick any point, plug the x and y value of that point in, and this will be a true statement. What you get on the left side will be greater than or equal to what you have on the right hand side. Okay. All right. Well, I think I'm going to do a couple more real quick. These two special cases, and then before we go to part 2. Okay. This is not a real long section. All right. So the two special cases. Well, you've got to remember that whenever we're dealing with a two-dimensional coordinate system, let me give you an example here. What if we just had a one-dimensional coordinate system? Well, that would just be a number line. Okay, and what if I wanted to graph x equals 4? Well, I would just find 4 on the number line, let's say it's right here, and I'd put a point right there, and that'd be it. Okay. But what if we want to graph this equation, x equals 4, on a two-dimensional coordinate system? Well, then what you're doing is you're plotting every single point that has an x coordinate of 4, okay? And there would be all kinds of those, right? But they would all have different y coordinates. And so if you were to do that, you would basically get a vertical line stationed at 4, okay, just like this. I'm going to erase this, by the way. Okay, because see, every single point on this line would have an x coordinate of 4. We don't care that the y coordinates are different because my equation doesn't have a y variable in it. Okay? So what I'm trying to get at is that anytime you have an equation that just says x equals and there's no y, you're going to get a vertical line. Okay? And similarly, if you have an equation that just says y equals, you're going to get a horizontal line that goes to the y-axis at whatever that number is. Okay? That just means that all of those ordered pairs would have the same y coordinates and all different x's. Okay? All right, so that's what you need to know for this little area or section here. Well, I guess I could have kept those, but does it allow me to? No. Well, never mind. Okay, so what about an inequality that just says x is greater than 2? Well, initially you're going to treat it like it's an equation, just x equals 2. So where would that be? Well, it would just be stationed right here. It should be made up of all these points that have x coordinates of 2. Okay? So it's going to be a vertical line, but what kind of vertical line? It is going to be dashed, because that's a strict inequality. Okay? So what I need to do is draw a vertical line that goes through the x-axis at 2, and that is dashed. Okay, so there it is, right there. Now, we still need to shade. We need to shade a region. It's either going to be to the left or to the right. Well, guys, where are all the ordered pairs that have x coordinates that are going to be greater than 2 going to be? They're going to be to the right of this line, aren't they? Because they'll all have x coordinates greater than 2. So we're going to shade to the right. Okay. Okay, so that's a case in which it's just x is greater than or whatever to just some number. There's no y. Okay, so you're going to get a vertical line. Now let's look at the second case. All right, so all these ordered pairs here, not the ones on the line, because the points on the line have coordinates in which x is equal to 2, and that's not what this says. This says that x is greater than 2. So it's all the points to the right. Okay, so what about a second case? What about right here? Y is less than or equal to -4. Okay, so again, let's first treat this like it's an equation. Y equals -4. Okay, well, where would all the points that have y coordinates of -4 end up? Well, they would end up all along here. Okay, so we get a horizontal line. Now, is this going to be solid or dashed? Well, let's look at our inequality symbol. It is a non-strict inequality symbol. So that means it'll be solid. Okay, so there's my solid line. Now where are we going to shade? Well, let's look back at our inequality. It says y is less than or equal to -4. Well, where are all the ordered pairs that have y coordinates that are less than -4 going to be? They're going to be above or below this line? They're going to be below. That was a rhetorical question. Okay. But because that inequality symbol said less than or equal to, we're also including the points on this line, because the points on this line have y coordinates that are equal to -4. Okay. All right. So guys, I think I'm going to stop there for part 1. And in the part 2 video, I'll show you, because you should be watching the videos in their entirety before starting the homework. So at the end of part 2, I'm going to do a homework exercise for you just to show you how to get the how to make the line either solid or dashed, and then how to show you how to shade the region. Okay. So in the next part 2, we're going to be looking at graphing a system of linear inequalities. So just like a system of equations, except it's a system of linear inequalities. So it would be a region that satisfies both of these. Okay, I've got a little example here. So it's just one last example, and then we'll look at a homework problem. So I'll see you in the part 2.